All right, this is a review we did yesterday, which we didn't cover that much because there wasn't much to cover. But basically, this is what the whole thing is about. Finding the area under a function. So first off, let's look at what we're talking about here. We're looking at the sine function from 0 to pi. So we have pi over 2, pi, 3 pi over 2, and 2 pi. It ranges from 1 to -1. At 0, sine is 0. At pi over 2, it's 1. 3 pi over 2 is -1. We're only looking at it from 0 to pi. We want to know what this area is below here. The area is everything under the curve between the x-axis and the curve, everything below the function. Now, this is the point, this is the part where you have total control on. You could decide on how many intervals to have. If you only do 2 intervals, then we'll only have 2 parts, but it won't be too accurate. The more intervals you have, the more accurate it becomes. Remember, area is base times height. So in our case, the height is how far it is from the x-axis to the function. So that's our function. What's that? What's that? We're looking for the area under the curve. This here is this whole area here. No, this is the whole area. We're building up. We look at the big picture first and then break it down. We're going to break it down into these smaller sub areas. So the height is known by the function. The base is how wide each of those intervals are. If we look at it this way, because if we look at it as one entire unit, the base is pi. The height is 1. So the area is pi. Which is 3.121814. Let's look at it with 4 intervals first. Say that n equals 4. So what we have to do here this is going to be pi over 2. This is going to be pi over 4. 3 pi over 4. Our delta x will be the interval between 0 and pi over 4, between pi over 4 and pi over 2, the interval between pi over 2 and 3 pi over 2, and then 3 pi over 2 pi. But fortunately, they're all the same height. I mean, all the same width. To make sure that we include all of our function in all of our intervals, we have to look at this in a special way. Because you're right, we're going to make rectangles. So our first rectangle will be this one. 4. Yeah, it's there. And then here we have another interval. And then here we have another interval. So this value is f of pi over 4. The next one is at f pi over 2. That next one is at f pi over 2. And then the last one is at f of 3 pi over 4. So our area is going to consist of each of these areas here. So we have the first one at pi over 4 times delta x plus f of pi over 2 times delta x. And the third one, f of pi over 2 times delta x. And then the last one, f of 3 pi over 4 times delta x. Because these are my inputs. So we can condense these since we have the same formula pretty much. Since we're adding them, and it's all f of x times delta x, this is how we can do it. Where k is our index, and n is how many intervals we want to have. So for our case, what's our function? Our function is the sine of x. So we're going to have, and since all of the intervals, the delta x's are the same, we can bring those out in front. So all we're going to do is add up all of these and then multiply by the delta x. So how do you find delta x? Delta x, here's the formula for delta x. It's b minus a over n. Because you're looking at what delta x represents is we're taking the entire interval and cutting up into how many spaces. So in our case, it's pi minus 0 over 4. So delta x in our case is pi over 4. In this small example here. So we get pi over 4. So the first one, we have sine of pi over 4 plus sine of pi over 2 plus sine pi over 2 plus sine 3 pi over 4. Let me copy that side. So we have pi over 4 sine of pi over 4 sine of pi over 2 sine of pi over 2 plus sine 3 pi over 4. Why do I have pi over 2 twice? Because look at our picture. We always want to include the graph inside our interval. Normally, we did it on the upper end. But on the downward slope, we have to do it on the lower side to incorporate it. So we use the pi over 2 for this one, and we use the pi over 2 for that one, for the height. So we have pi over 4. Sine of pi over 4. Square root of 2 over 2. Sine of pi over 2 is 1. Sine of pi over 2 is 1. Sine of 3 pi over 2 is square root of 2 over 2. It's in the second quadrant. So add those. We have 2 square root of 2 over 2 plus 2. The 2's cancel. So we have square root of 2 plus 2. And there's your area. And in our initial example, I said 8 intervals. So our delta x would be b minus a over 8. Pi minus 0 over 8 makes it pi over 8. That's our delta x. We have 1, 2, 3, 4, 5, 6, 7, 8 intervals. So this is 1 pi over 8, 2 pi over 8, pi over 4 in this case, 3 pi over 8, 4 pi over 8, 5 pi over 8, 3 pi or 6 pi over 8, 7 pi over 8, and then 8 pi over 8. Notice how whenever we have a dome, the middle point will be counted twice because we have to have one for this side and one for this side at pi over 2. Since our delta x is always going to be pi over 8, we can put that out in front. It's never going to change. Now, these are our inputs for the function. So we have sine of pi over 8 plus sine of pi over 4 plus sine of 3 pi over 8 plus sine of pi over 2. Since that's the middle, we got to do it twice. Sine of pi over 2 again. Five pi over 8. Three pi over 4. Seven pi over 8. 3, 4, 5, 6, 7, 8. We have to have 8 of them because we have 8 intervals. So pi over 8. So 180 divided by 8, 90 divided by 4, 45 divided by 2, 27.5. So we got to use a calculator here. But yeah, so pretty much that's all you do next is use a calculator. We know that one is going to calculator wise. Sine of pi over 4 is square root of 2 over 2. 3 pi over 8, we're going to do that one. And that's 1. That's 1. Then sine that. And that's square root of 2 over 2. And then that one. So I just calculated the easy ones. 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. So these other ones have to be calculated by calculator. These last four. But add them up, divided by 8, times pi, and that's it. And you'll see that our value gets closer and closer and closer to pi, or to our true area. So how can we get to exactly right size? Because if we calculate this and we calculate this number is going to get closer. So how can we get even closer to the actual area? Well, let's look at this. This one, we only had 4 intervals. This one, we had 8 intervals. So how can we get a better answer? What's the best answer we can have if we have how many? Infinite. So if we have an infinite number of intervals, then if we take the limit as n goes to infinity, and in order to get the best answer for each of our intervals, if we took the midpoint, let's call that C. So that's C1, that's C2. If we take the midpoint at that value there, we'll have short on one side, but too much on the other side. So where C is the midpoint of each interval, x1 to x2, or xn to xn plus 1. What is going to happen with this equation? What's going to happen to delta x? Remember, delta x is b minus a over n. As n goes to infinity, eventually delta x goes to 0. We're going to have an infinite number of, instead of rectangles, we're going to have lines. Then we add up all the lines, and then that'll give us our area. That's called the Riemann sum. It subdivides any curve into small rectangles and makes them infinitely small so you can add them all up, and that'll give you the true area under a curve. It'll any function you have, it'll to find the area, it'll subdivide that curve into an infinite number of infinitely small intervals, and then it'll add them up, and then as n goes to infinity, it'll give us a true area of under that curve. So that's what that whole thing does there. All right, so that was a summary of the first section. Now, in section 2, Are y'all familiar with the summation symbol? What it does? Okay. Then I apologize for this part up here. This is called sigma in Greek, summa in Latin. Summa simply means add all together. You're taking the sum of all the data. Yes, yes. This is your index. This is your starting point. Starting value or starting point. And this is where you end. Or the ending value. It doesn't have to start at 1. You can put any negative number. You can put any positive number. You can put 0 in there. And n can end anywhere. It can even go to infinity. So let's look at this. X sub k. K equals 1, 2, 4. This is my data set. Since my data set is defined as X, each one of these, their location is defined by a subscript. X sub 1, X sub 2, X sub 3, X sub 4. Where the subscript tells us the location of that number. X sub 3 is the third number in that sequence. So the subscript tells us the location of that number. The second number, X sub 2, is equal to 3. So the summation of k equals 1 to 4 of X sub k. What this means, my k starts off at 1. So I go X sub 1. Then I go to the next one, X sub 2, X sub 3. I stop when X gets to k gets to 4. So my X sub 1 in my data set is 1, X sub 2 is 3, X sub 3 is 5, and X sub 4 is 7. Add them up, I get 16. That's all the summation symbol's about. Okay, same thing there. Let's try k equals 2 to 5 of x squared sub k. Okay, so what this thing says, I start off with 2, so it's x sub 2 squared, x sub 3 squared, x sub 4 squared, x sub 5 squared, and I stop at 5 when k is 5. So x sub 2 is 3. I square it. X sub 3 is 5. I square it. X sub 4 is 7. I square it. And x sub 5 is 9. And I square it. So I square each of those and then add them together. 9, 25, 49, 81. 90, 139, 159. It's 164.
So whatever
The index.
yeah, oh, sorry, the next part.
Yeah, this is the index.
Yeah, why start from starting point?
Because my first K is 2, so my subscript is x sub 2. That means it's my second data point. There's my first point, there's my second point. That's third. So remember, the index, the subscript represents the location. And that's the location of this.
And you can put whatever function you want in, like with X squared.
Right. Yeah, it could be anything. It could even be for example, the function f of k, where k is equal to 1 to 5. That would be f of 1, f of 2, f of 3, f of 4, and f of 5. Oops. Okay, here we have example 1 in your packet. Note sheet. Example 1. Summation of k equals 1 to 5. Summation k equals 1 to 3. Excuse me. Yeah, thank you. Summation of k equals 1 to 2. K over k plus 1. And lastly, k equals 4 to 5. Written out. And the value. All right, so what does the first one tell us? Since our k is the index, it's asking us for k is 1, starts off at 1, again goes to 2, then 3, then 4, then 5. We have 6, 12 equals 15. Now the next one. We have -1 to the power 1 of 1. plus -1 to the power 2 of 2 plus -1 to the power 3 of 3. So I'll go from 1 to 3. -1 to the first power is -1. -1 times 1 is -1. -1 squared is positive. +1 times 2 is 2. -1 cubed is -1 times 3 is -3. So we have -4 plus 2 equals -2. And the next one, k starts off at 1, so it's 1 over 1 plus 1 plus 2 over 2 plus 1. Makes it 1 over 2 plus 2 over 3. Add those. I get 7 over 6. And the last one, we're going from 4 to 5. So the first one starts off at 4 squared, 4 minus 1, plus 5 squared, 5 minus 1, 16 over 3, plus 25 over 4. $64.75. 64% power is 139 over 12. Pretty straightforward. You just have to keep track of where your numbers are. All right, let's look at example 2. Now we got to do a little bit more work. Example 2. This is example 2. Express the sums of 1, 3, 5, 7, 9 in sigma notation, starting at k equals 0, k equals 1, k equals 2, and k equals -3. One plus 3 plus 5 plus 7 plus 9 in sigma notation. K equals 0, k equals 1, k equals 2, k equals -3. Okay, so our numbers are 1 plus 3 plus 5 plus 7 plus 9. This would be the same for all of them. The only difference now we have to come up with a sigma notation, a formula. So when we start off at 0, our function will get these values. So if it starts off at 0, where does it end? This is k sub 0, k sub 1, 2, 3, 4. So this one ends at 4. Yep, so we know from 0 to 4 is 5. We have to have 5 elements. So now we have to come up with an equation. We have to come up with an equation that when k is 0, we get 1. When k is 1, we get 3. When k is 2, we get 5. When k is 3, we get 7. And when k is 4, we get 9. Actually, when I was saying that, it came up what it should look like. So when k is 0, we get 1. When k is 1, we get 3. Think about this. When k is 1, we get 3. When k is 2, we get 5. K is 3, we get 7. So what's the formula? So whatever k, this is k equals 0. K is 1. So if we double 1 and then add 1, if we double 2 and add 1, if we double 3 and add 1, and we double 4, we add 1. So that's the formula for it. Okay, now we have to come up with another equation. When k starts at 1, it goes to 5. This is when k is 1, k is 2, 3, 4, 5. If it's 2, we get 3. If it's 3, we get 5. If it's 4, we get 7. It's 5. How do these all relate? If we double 2, how do we get 3? If we double 3, minus 1. So the answer is 2k minus 1. No, this one starts off at 2. 2, 3, 4, 5, 6. So this one goes to 6. 2, 3, 4, 5, 6. So what equation, if this is our k, that we get 1 after it's said and done? So all the other ones, we doubled it. So 2 times 1 is 2 minus 1. 2 times 0 is 0 plus 1. So 2 times 2 is 4. How do we get 1? Okay, so let's get, so we minus 3. 2 times 3 is 6 minus 3. 2 times, yep. So 2 times k minus 3. And this one starts at negative 3. So it's negative 3, negative 2, negative 1, 0, 1. So it stops at 1. So these are my k values. Negative 1 minus 2. No, that won't work. So let's try double these. If we double these, we get negative 6. How do we get 1? We have to add 7.
Thinking,
Negative 4, yeah, negative 7, a negative 2 plus 5, yeah. So it's 2 times k plus 7.
Yeah. In that case, since there's a zero.
That's true. That's,
why I
yes.
was looking at that. I need a little bit more. Sorry.
No, as I didn't get that far yet, but yes, you're right. If you have a 0, that tells you what to add. Perfect, yeah. Like the first one. We had 0, so we know we have to add 1. The algebraic rules for finite sums. When we say algebraic rules, what do we mean? Add, subtract, multiply, divide, those kind of things, the binary operators. We always have a sum rule that says this. If we have a sum of 2 numbers, subscripted k, we can separate those into 2 separate ones. Different rule. Same thing, but instead of plus, we have a minus. The constant multiple rule says that if you have some constant in front of your number, that constant can come out in front. Then you could do the operation. So constant simply goes out in front. The constant value rule. And this just goes straight from the basic rules of elementary school math. Multiplication is simply the addition of the same number over and over. So what this he says is if I have C and I add it together n times, it becomes n times C. All right, let's look at the next set of examples. Example 3. Demonstrate the use of the algebra rules. Okay, A is K equals 1 to N of 3K minus K squared. So this is the difference rule. So we have the summation of K equals 1 to N of 3K minus summation K goes from 1 to N of K squared. We have a constant multiple, so that 3 goes out in front. So 3 times the summation of K minus the summation of K squared from K equals 1 to N. There's the answer. The summation of negative A sub K. So which rule do you think we're going to use here? Yep, it's a constant multiple. Very good. Because what we have here is a negative 1. This negative goes out front, it's a negative 1. So that equals negative A sub K summation of K goes from 1 to 3 of K plus 4. This is a sum rule. K, summation of K goes from 1 to 3. And the summation of 4 as K goes from 1 to 3. Well, this one we can calculate out because there's no function we don't know. And it's a finite range. So the first one is 1 plus 2 plus 3. That's that one. Plus the next one, since it's a constant, the summation of a constant is that constant times n, 4 times 3. 6 plus 12 equals 18. Remember, we couldn't do that to the other ones because we never knew what n was. Here we have a finite domain. Summation K goes from 1 to n of 1 over n. Notice there's no K inside there. So 1 over n is a constant number. So we take 1 over n times n, which becomes 1. These cancel. So far, so good?
Is there a portion rule?
No. Because. Well, actually. Let me think about that. Is there a product or a quotient rule? Let me think about those. I have to work those out. Because you'd have to add up the sum of the top and bottom first. The difference would be this. Do I sum the quotient first through all the k's, 1 through n? Is that gonna be the same as adding up all the numerators and all the denominators? Which I don't think is gonna be right, because in order to add the fractions, you have to have a common denominator.
Right.
So no, you can't do that. Example 4. Show that the sum of the first n integers is. Actually, yes, because had you had me for algebra, we would have discussed a process by a guy named Gauss, who was like 12 or 13 years old. No. That's matrices. He was a super smart kid. He knew more than his teacher did. And he kept on always asking questions and pretty much counterfeiting the instructor. The instructor got tired of him once and said, okay, go outside. Don't come back until you add up all the numbers from 1 to 100. Okay, so this is what he did. He looked at, so instead of looking at the big thing, he looked at the smaller ones. So let's look at 1 plus 2 plus 3 plus 4. So that's going to be 10. There's got to be a formula. Let's go to 6. 1 plus 2 plus 3 plus 4 plus 5 plus 6. That equals 21. Okay, how can I speed up the process? What he realized, if I take the first and last numbers and the next ones, they all equal the same numbers. So the sum of these numbers is always going to be 5. How many pairs of numbers do I have? Since there are only 4 of them, I have 2 pairs, so 5 times 2 is 10. Same thing here. The first and last number is 7, and we have 6 numbers. So if we take 6 and divide by 2, we have 3 pairs, which is equal to 21. So from 1 to 100, he figured out it's 101, and they occur 100 divided by 2 times. So 101 times 50. The answer is 50-50. In about 3 minutes, he came back in the room and gave the instructor, and the instructor didn't believe him. So he showed him how to do it. So this is how, and this is, if you look at it, since we always start at 1 and go to 100. How many numbers are there? 100 numbers. So there's n. So we had n over 2. This one is n plus 1. It's always going to be n plus 1, which makes it n times n plus 1 over 2, which is what we have here. And that's the summation, no matter what that is. But what they want us to do is to show it out. And this is how we would show it. If n was 4, we'd have 4 times 5 over 2, which would be 10. So that's how we would prove it.
That's going to end up providing like some sort of accounting strategy for small business.
Actually, all of them did back then because commerce was, so everybody had to figure out the way to do it. Well, see, back then there were a lot of geniuses, Gauss, Riemann, all these, I mean, just name it, all the big names of math back then. Same. Euler, yeah. So yeah, and he's one who's very big in numerical analysis.
Yeah.
So we know that here we have our first example. So we can go from a summation to a straight up formula. But we can go further now. If we have the summation of k squared from 1 to k, we can expand that to be n plus 1, 2n plus 1 over 6. So there's that formula. Then we can go one step further. K cubed. K cubed So note these three formulas, because we'll be using those in the next few examples. So make sure you make note of these three formulas. So let's use these in example 5. Finding the limiting value of lower sum approximations to the area of the region R below the graph y equals 1 minus x squared and above the interval, so it's on the interval 0, 1, above the x-axis. On the x-axis using equal widths rectangles whose widths approach 0 and whose number approaches infinity. So as n goes to infinity, delta x goes to 0. That's what it's saying. So what is delta x? Remember, delta x is always b minus a over n. 1 minus 0 over n. So delta x is equal to 1 over n. So if we look at this, what this graph looks like when x is 0, y is 1. So it goes like this. It's a downward parabola. And we only want this area. So our summation will have to be 1 over n, because that's how many intervals we have it. These are all our intervals. Times delta x. One over n, or k over n times 1 over n. Yeah, this has to be k over n, because the k is all of our intervals inside there. Now, like it said, we have to use, where that? Find the limiting values of lower sum approximation. Lower sum approximation. Why do we have to use lower sum approximation? And what is lower sum approximation? Lower sum approximation, so here's our interval. Here's our first interval. That rectangle will have to be on the lower side. The reason being because we cannot use 0 as an n. Because at 0, it's undefined. So we got to use the lower sum, which is 1 over n. So let's plug in all this. Now we have our function. Let's put this in there. So this is our f of x, 1 minus x squared. So we get the summation as k goes from 1 to n of f of n minus n over k, which is this function, 1 minus k over n squared times 1 over n. So far, so good. So we have 1 minus k over n squared. Distribute that inside there. So we have 1 over n minus k squared over n squared times 1 over n. One over n minus k squared over n cubed. This is the difference rule. So we have summation of k equals 1 to n of 1 over n, k squared over n cubed. So that becomes summation as k goes from 1 to n of 1 over n minus summation of k equals 1 to n of k squared over n cubed. The first one. What do we do with the first one? One over n is a constant because what n's are terminating number. So what do we do with a constant? We multiply it by n. If this was 5, it'd be 1/5. How many times is it added? 5 times, so it's 1/5 times 5. Now this one, look at this. This is a constant, so it could be brought out in front, n cubed. So all we really have to deal with is the k, or k squared. So the n's cancel, so we have 1 minus 1 over n cubed. Now, what is this? If we expanded this, what would we get? Yeah. K squared, yes, so it's n plus 1, 2n plus 1 over 6. Because now we got rid of all the k's. Now we're just at n. Okay, so what can we do now? This n and one of these can cancel. We have 6n squared on the bottom. We can go ahead and multiply this out. So 2n times n is 2n squared. 1n plus 2n is 3n plus 1. Okay. So now what do we do? Now we have a formula. What is n going to? As n goes to infinity, we get the limit as n goes to infinity of our equation. 1 minus 2n squared plus 3n plus 1 over 6n squared. So that gives us 1. Since these are both n squares, we get 2 over 6. It's the horizontal asymptote. Do you see why you get 2 over 6? Because this equation here, this part here, we can expand it to 2n over 2 over 6n squared plus 3n over 6n squared plus 1 over 6n squared. As n goes to infinity, these have more on the bottom, so they go to 0. These cancel, so we have 2 over 6, which makes it 1 minus 1/3. 3 over 3 minus 1 over 3 is 2 over 3. That is the area under the curve. Okay. Whenever you have a function When we deal with areas under curves. Whenever you have a function f of x on some domain, it's not really anywhere, but this is what I suggest you doing. Determine if there are any x-intercepts in the domain. And here's the reason why. Let's look at our function sine x going from negative pi to pi. Oh, let's go negative 2 pi to 2 pi. Let's go all the way out. Pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. 1, negative. Pi over 2, pi, 3 pi over 2, 2 pi. Actually, let's go from 0 to 2 pi. That I don't do extra work. So at 0, we get 0. At pi over 2, we get 1. At pi, at 3 pi over 2. If we looked at this area of this function from 0 to 2 pi, you know what the area would be? The area would be 0. And here's the reason why. Because you notice this area up here? This area is positive. This area is below the x-axis, so that area is negative. They're both the same size. So when you add positive and negative of the same size, what do you get? 0. So once if you have your equation and you come up with the area of 0, that means that you have an x-intercept somewhere along the line where the two sides are equal.
So periodic functions most of the time?
Always periodic functions. Depending on the domain, because if we went from 0 to pi, no problem. But if we went from negative pi to pi, then this would be down here, that would be up, they're opposite each other, and there'd be 0 again. So that's why I said, look to see if there's inside the domain, are there any x-intercepts? No, because now that you're above the x-axis, because these values down here are all negative. If I shift it up, they're all positive.
That's what I mean, is that you feel that there would be a value that isn't zero. It's above that. Right? So there,
Let me see this. So this one. it'd still give you zero. Because it's simply because relative to where it is. So how can we determine if there's a zero between there? So where is sine x, where is it equal to 0? When x is equal to pi. When x is 0. When x is 2 pi. So these are all, so the only place we have an x-intercept, these are our endpoints. What you do there now, if that's the case, then do them both separately. Do 2 of them. And then this will give you a positive area, this will give you a negative area. Take the absolute and then add them together. If your intervals, if your delta x are not the same size, there are situations where it can occur. If that's the case, then, well, first off, then take the norm of the partition. Here we're introducing 2 new words. Partition is simply all of your domains, I mean, your intervals from x sub 0 to x sub 1, x sub 1 to x sub 2, x sub 2 to x sub 3, and so on and so forth. Those are partitions because you've taken the domain from A to B. You label the first one x sub 0 and the last one x sub n. And we divided that. So this will tell us how many partitions we're going to have. Number of partitions. So whenever you hear the word partition, you're simply talking about the width of the interval. Now, remember, these are not the same size. So now here's a question I ask of you. If they're not the same size, which one, because you have to use one and only one, which one do you use? Do you use the smallest or do you use the largest? And why? You can't use the smallest because if you use the smallest, then anything bigger is going to be, you have all the extra space wasted. And so it won't be exact. But if you use the largest, even the smaller ones will be contained in there. So that's what the norm is. The norm is these 2 lines on both sides. The largest partition. So the norm is represented by this. It represents the largest partition. And that's going to be your delta x. Example 6. Here's our set of partitions. 0, 0.2, 0.6, 1, 1.5, and 2. It's a partition of our interval 0 to 2. So what does this represent? These are, what these partitions mean, these are the points along the line. So our first interval will be from 0 to 0.2. The next interval will be from 0.2 to 0.6. The next one is from 0.6 to 1, from 1 to 1.5, and then from 1.5 to 2. Find the norm. So the way you do this is find the length of the intervals. So it's 0.2 minus 0. This one is 0.2 units long. 0.6 minus 0.2, that's 0.4. 1 minus 0.6, that's also 0.4. 1.5 minus 1 is 0.5. 2 minus 1.5 is 0.5. So these are the width of the intervals. So what's our norm? What's the biggest one? Yep, so that's our norm. All right, that's it for that section. We have sections 2, 3, 4, 5, and 6, and we're done. So if everything goes right, we'll be done this week.